All right, in this example, this will be another application of torque equals R perpendicular F. We'll see that in a lot of these examples, really, the R perpendicular F formulation is preferred over the F perpendicular R relationship. So a lot of times people get a little confused as to how to get R perpendicular. But we'll get lots of practice with it on this problem. Okay, so here we have a monkey climbing a ladder. Let's assume that the ladder is at a 60-degree angle to the horizontal. Okay, and so the monkey, though, is concerned, but is still willing to give it a try. And so the monkey is climbing the ladder, gets to a certain distance x, and so let's find the distance x when the ladder starts to slide. Okay, so the monkey then, when it gets up to a certain point, the ladder, actually it may or it may not slide. You know, if we do our algebraic solution and we get a value for x that's longer than the length of the ladder, it means that the monkey makes it. If we get a value for x that's less than 0, it means the ladder slides before the monkey ever gets there. So it's only if the value of x is between 0 and the length of the ladder that the monkey will actually slide down along with the ladder. So we're not necessarily hurting the monkey in this example. You know, where you're going to have to figure, as a matter of fact, I'm going to set the equations up for you. I'm going to have you solve them for some practice. Okay. So what we want to do first in this problem is to, of course, identify all of the forces that are acting on the ladder. Okay, so it's the ladder that we're interested in. Let's say the mass of the monkey is equal to 50 kilograms, and let's say the mass of the ladder is equal to 25 kilograms. Okay, so we're going to have some forces that are acting down. This is going to be mass of the monkey times g, and then at the L/2 position, we'll have the mass of the ladder times g. In the vertical direction here, we're going to have F normal ground. Okay, so that's the normal force exerted on the ladder by the ground. And push up that way. And because I think we can see here that the ladder is going to tend to slide out this way, we're going to also have a force due to friction, S static maximum. So we're going to push that friction force to its maximum value, and at that point the ladder will start to slide. If we exceed that force as the monkey goes further and further up the ladder. And then finally we have a force acting in the horizontal direction here, which I'll call F normal wall. Okay, so we have F normal on the ground. Also here I have F normal wall. And in a more advanced problem, we would also have friction on this surface, which would mean that we would have a force of friction on this top surface as well. But that will be a smaller force of friction because F normal wall is going to be a lot smaller than F normal on the ground. And so I'm going to neglect that part of the problem just because it's tough enough already. And so we'll assume that the wall is frictionless and that there's only friction on the ground surface. Okay, so have we got all the forces now that are acting on the ladder? The answer is yes. The two forces, here's in the center of mass for the ladder. That's at the 5-meter position. The length of the ladder is 10 meters. The monkey, we don't know where the monkey is going to be, so we'll just call that distance x. But it could be anywhere. It could be all the way up or down. And then we have F normal ground, and we have F static maximum on the bottom surface. So what do? Well, first, because we're not familiar with the torque problem, just to give ourselves a little bit of time to think about the torque aspects of this, let's do the force equations first. Okay, so I'll have the sum of the y forces is equal to 0. So what have we got here for a y force? We've got F normal ground. We have, well, these two forces are vertical. So it's going to be minus mass of the monkey times g minus mass of the ladder times g equals 0. Okay, so those are our only y forces, are the two weight forces and the normal force from the ground. Okay, now in the x direction, we have the sum of the x forces is 0. And I think it's clear here that we've chosen an xy coordinate system that looks like that, because all the forces are either vertical or horizontal. None of them are off at an angle in this problem. Okay, so the sum of the x forces in, we have F static maximum minus F normal wall equals 0. So it's this force minus that one is equal to 0. Okay, so we don't have enough information yet to find x from either one of these equations. You can use this equation to get F normal ground. So F normal ground will be the sum of the masses times g. And then once you have that, then you can get the F normal wall, because this is the coefficient of static friction times F normal ground. Minus F normal wall is 0, and you have F normal ground from the stop equation. So you can get the static friction force, the normal force here from the ground, and the normal force from the wall from the two force equations. But that doesn't get us any closer to solving for x. So what we need are torque equations for that. Okay, and so what I'm going to do here is, for the torque equation, we're going to choose R perpendicular F for our torques. Why? Because all of these forces are already oriented in the vertical and the horizontal direction. And so if I start taking components of that that are along the ladder, I've got to decompose every single force vector into x and y components, and it's going to get to be a confusing mess. And even with the experience that I have with doing these problems, I'm afraid that with that level of confusion, I'm going to make a mistake. So I'm not going to do it that way. What I'm going to do instead is I'm going to extend the force vector lines, for example, with the monkey. I'm going to extend this force vector line. Then I'm going to draw a line that goes from my pivot point, which I'm going to choose to be here, just because that kind of seems like a good pivot point. And it's also, I'm measuring x from that point. So that means I don't have to redefine x. Okay? If I measured it from some other point, then the value of x is measured with respect to this point here. Okay? And so then I might make a mistake when I'm translating x into that new coordinate system with that new pivot point. So I'm going to choose it such that x is defined the way that I want it to be defined, because I don't see any other advantage in choosing it any other way. Okay, so this is my pivot point. It also seems like it might be pivoting about that point, so it gives me a little better feeling for the problem. And so measured with respect to that pivot point, I can extend the force vector line for the mass of the monkey and then draw this R perpendicular so that it comes in perpendicular to the force vector line. So remember, that's how we did it in the last example, and that's the way that I did it in the kind of generic example that works for any problem that uses this form for the torque equation. So now I'm going to set myself up with a table of clockwise and counterclockwise torques. I'm going to see here that the monkey, with respect to this pivot point, and the ladder both make the system want to go clockwise. Okay, so this is going to be mass of the monkey times g, and then this distance here is x, so this distance here is x cosine 30, or 60, x cosine 60. So the x cosine 60 is very simply this distance here. This is x to the monkey. This is 60. I'm drawing the force vector line, so this distance, which is our perpendicular here, is x cosine 60. Similarly, I can do that with the mass of the ladder times g. That's mass of the ladder, g. Now this distance, though, because we're going to the center of mass of the ladder, is going to be equal to L over 2 cosine 60. Okay, so that's this distance here. This is L over 2. So this distance here is L over 2 cosine 60 from here to there. So that's my R perpendicular. I've extended the force vector line. I've drawn an R perpendicular so that it intersects it at a 90-degree angle. So this distance, L over 2 cosine 60. That's the part that I think gets people the most, is just not getting the geometry and you're not following those instructions. But if you follow those to the letter, then you're not going to make a mistake here. And then finally, we better have a third torque that produces a counterclockwise torque. Because if they're all clockwise, that means the monkey slides before we even get started. And so we don't want that to happen. It's not going to happen in general, because here we've got F normal wall. So what do? First of all, we ensure that that produces a counterclockwise torque. Sure enough, we apply a force this way. That makes the system want to rotate counterclockwise. This gives us F normal wall. And so then are we looking at this distance? No. Don't just go with the flow here, because this was L over 2 cosine 60 and x cosine 60. You might think, well, this is L cosine 60. No. You have to follow the rules. You extend the force vector line, then you draw a line that goes from the point that we're calling the pivot point so that it intersects it at a 90-degree angle. So that's this distance here. Okay, not this distance or that distance, but this distance. So that's going to be equal to L times the sine of 60. So that's going to be my R perpendicular here, L times the sine of 60. All right, so now what do we do in the next step? Well, we set the sum of the clockwise torques equal to the sum of the counterclockwise torques. So what we've got here then, we got 2 clockwise, mass of the monkey times g times x cosine 60 plus mass of the ladder times g times L over 2 cosine 60 equals F normal wall times L sine 60. Now you might be saying to yourself, well, in the last example I did, the L's canceled. And in the one before that too, the L's canceled. So are the L's going to cancel here? The answer is no, because we don't have an L in the monkey term. We just have an X. So that means we really do need to know what the length of the ladder is to get a solution to this problem. And because this is an equation that involves X, it also involves F normal wall. So let's go back over to these equations here. We can get F normal wall from this equation in terms of F static max, but F static max requires F normal ground. So you have to solve this first equation to get F normal ground, plug that into here to get F normal wall. And then you can take that value, plug it in there for F normal wall, and solve for X. So I'd like to leave that as an exercise for you to do. If you want to email me your solution, I can check it and make sure that it's okay, or you could just give me the answer that you come up with, and I can tell you whether the answer is correct. But what I'd like you to do with this is to solve for X and I want you to tell me whether the monkey makes it. So that's the question. Does the monkey make it? If x is less than 0, then the ladder slides without the monkey at all. It slides before the monkey even gets there. If x is greater than 10, the monkey makes it. But if x is less than 10, greater than 0, then the ladder slides at that point. So if the monkey doesn't make it, I'd like you to find the value for x and tell me what that value is.